everyone, what's up? Welcome back to my tutorial channel. Daniel's here, and today I'm going to talk about conditional probability and multiplication rule. So first, let's start off with conditional probability. So what is the difference between conditional and unconditional probability? Let's consider this example. Approximately 15% of adult men in the United States are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 0.15. Now assume that you learn that the selected man is a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall becomes much greater than 0.15. So at the first situation, without knowing that the man is a professional basketball player, the probability is 0.15. When we have an extra information that the man is a professional basketball player, the probability is much greater than 0.15. So the first situation is called the unconditional probability. That means the probability when we don't have any extra information. And the second situation is the conditional probability. That means we have an extra information that the man is a professional basketball player. So definition, conditional and unconditional probability. A probability that is computed with the knowledge of additional information is called a conditional probability. A probability computed without such knowledge is called an unconditional probability. So how do we compute conditional probability? So let's look at this example. Example 1 is how to compute unconditional probability. Let's say Joe, Sam, Eliza, and Mariah have been elected to the executive committee of their college student government. They must choose a chairperson, a secretary. They decide to write his name on a piece of paper and draw 2 names at random. The first name drawn will be the chairperson, and the second name drawn will be the secretary. What is the probability that Joe is the secretary? So for this problem, first we sketch off the symbol space. Here I'm going to use the first letter of his name to label these 4 people. So this is the symbol space consists of 12 possible elements, 12 possible outcomes. JS means Joe is the chairperson and S is the secretary because the first name represents the chairperson and the second one is the secretary. And similar for the others. Here the question asks for what is the probability that that Joe is the secretary. That means Joe should be at the second position in the pair, the order pair. Here we have 3 outcomes that have J at the second position. So for the outcome that Joe is the secretary, we have 3 order pairs, HJ, EJ, and MJ. So the probability that Joe is the secretary is 3/12, which is 1/4 or 25%. So that is about unconditional probability. Now let's look at a similar situation but conditional probability. Here everything will be the same. The problem is set up the same. However, we give an extra information that is suppose that Eliza is the first name selected. So she is the chairperson. Now what is the probability that Joey is the secretary? So in this case, when we look at the 12 possible outcomes, only the 3 outcomes in the third column right here are possible. because here one more information was given, that is Elisa is the first name selected. So only the events, only the outcomes that the letter E at the first position is possible. So we have EJ, ES, EM are the three possible outcomes. And the question asks for what is the probability that Joe is the secretary. There is only one order pair that represents Joe is the secretary in the possible outcomes. So we can rewrite the simple space as S prime. This is equal to a set of three possible outcomes, EJ, ES, EM. So the probability that Joe is secretary given that Elisa is the chairperson is 1/3. Here I use the notation P of Joe is the secretary dash, this is flash, Elisa is the chairperson is just 1/3 because we have one red outcome out of three outcomes. And this event, the event that given information that another event has already occurred is the given event. So given is a keyword to recognize the question for conditional probability. So now we learn how to compute a conditional probability. The conditional probability of an event B given an event A is denoted by P of B given A, and it is computed as probability that both event A and B occurs over probability that event A occurs. So the probability that B given A is the probability that B occurs under the assumption that A occurs. Let's consider example 2. So we are going to continue on example 2. Suppose that Elisa is the first name selected out of 4. So she is the chairperson. What is the probability that Joe is the secretary? So let's record a symbol space. This symbol space consists of 12 possible outcomes. And you can notice that the third column, the dot column right here, is a collection of all events in which Elisa is the chairperson. And the event in the red color, the outcome in the red color, is the event that Elisa is the chairperson and Joe is the secretary. So the red event is the event when both event A and B occurs. And the third column is the event when Elisa is the chairperson. So the probability that Joe is the secretary given Elisa is the chairperson is the probability that both event occurs over the probability that Elisa is the chairperson. The event that Joe is the secretary and Elisa is the chairperson is the red event. So the probability of it is 1/12. And the probability that Elisa is the chairperson is 3 out of 12. So the answer for the given probability is 1/12 over 3/12, which is 1/3. Multiplication rule. So from the conditional probability, we can derive the formulas of conditional probability to obtain the general multiplication rule. Remember, probability B given A is probability of A and B over probability of A. So if we multiply both sides with probability of A, we got probability of A and B is probability of B given A times probability of A. And also probability of A given B is probability of A probability of A given B is probability of A and B over probability of B. So probability of A and B is probability of A given B times probability of B. Example 3. Among those who apply for a particular job, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. find the probability that an applicant is offered a job. So for an applicant to be offered a job, there are two stages. The first stage is that applicant got an interview. And the second stage is after that person got an interview and passed, the person is offered a job. So being offered a job involves two events. First, a person must be interviewed. Then given that the person has been interviewed, the person must be offered a job. So using the general multiplication rule, we obtain probability that the person is offered a job is equal to probability that that person is offered a job given she is interviewed times probability that she is interviewed. So that is 0.25 times 0.1, and the answer is 0.025. Next, independence. So when are two events said to be independent? Two events are independent if the occurrence of one does not affect the occurrence of the other events. In other words, two events are independent if the probability of one to be occurs does not affect the probability that the other event occurs. If two events are not independent, we say they are dependent. Let's consider example 4. A fair coin is tossed twice. What is the probability that the second toss is a head? So when a fair coin is tossed twice, no matter the first time the coin landed head or tail, for the second time there's only two possible outcomes, either head or tail. So here the probability that the second toss is a head is 1/2. What is the probability that the second toss is a head, given that the first toss is a head? Here again, like no matter what happened with the first toss, for the second toss we only have two possible outcomes, head and tail. So the probability of getting head at the second time given getting head at the first time is still 1/2. So here we notice that the second toss is a head. This event will not change if the first toss is a head or tail. That means the first toss does not affect the second toss. So here we say the event that the first toss is a head is independent with the event that the second toss is the head. So for independent events, we also have multiplication rule. If A and B are independent, then probability that both of them occurs is probability of A occurring times probability of B occurring. And this rule can be extended to the case where there are more than two independent events. Let's say A, B, C, and so on are independent events. Then the probability that all of them occurs is probability of A occurs times probability of B occurs times probability of C occurs, and times so on. Example 4. According to recent figures from the U.S. Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, 26% in Los Angeles. If one person is selected from each city, what is the probability that all of them are under 18? Is this event an unusual event? So here, each city we are going to select one person at random. And the probability, let's say I'm going to select the person A from New York City, B from Chicago, and C from Los Angeles. So the probability that all of A, B, C are under 18 is the probability that A is under 18 times the probability that B is under 18 times probability of C is under 18. So the probability that the person from New York City is under 18 is 0.235. The probability that the second person from Chicago is under 18 is 0.258, and the probability for the third portion from Los Angeles to be under 18 is 0.26. So multiply them all together, we got 0.0158 is the probability that all of them is under 18, and this probability is less than 0.05. So this is an unusual event. So that is everything about multiplication rule and conditional probability. Now we are going to do some practice. Let's consider sampling without replacement. A box contains 2 cards marked with a 0 and 2 cards marked with a 1. 2 cards will be sampled without replacement from this population. Without replacement here means the first time we withdraw 1 card and throw it away, and then continue withdraw another card from the remaining cards. What is the probability of drawing a 1 from the second draw given that the first draw is 0? So here, if the first draw is a 0, so we took 0 out, we have only 3 cards left, 1, 0, and 2 number 1s. So the probability that the second draw is a 1 is 2 out of 3 because we have 2 cards of number 1 and 1 card of number 0 left. So the probability of drawing a 1 from the second draw given the first draw is 0 is 2/3. What is the probability of drawing a 1 on the second draw given that the first draw is 1? So in this situation, the first draw is 1, that means we took number 1 out. There are 3 numbers left, 2, 0, and 1, number 1. So the probability of drawing a 1 from the second draw is 1/3. So you see that the event that the outcome of the first draw does affect the outcome of the second draw, because if the first draw is 0, the probability of getting 1 as the second draw is 2/3, but if the first draw is 1, the probability of drawing a 1 on the second draw is 1/3. So here, the occurrence of the first draw does affect the occurrence of the second draw. So the first draw and the second draw are not independent, they are dependent. So the answer is no. So for sampling without replacement, events are usually dependent. And now we consider sampling with replacement. So just similar to the last problem, but here the process of withdrawing the cards is with replacement. So a box contains 2 cards marked with a 0 and 2 cards marked with a 1. 2 cards will be sampled with replacement from this population. What is the probability of drawing a 1 on the second draw given the first draw is 0? Here, because those cards withdraw with replacement, so the first card were taken out and then put it back. So no matter what happened with the first draw, whether it's 0 or 1, is still back to the box. So the probability that the second time getting a 1 is still 2 out of 4 because we still have 2 number 1s and 2 number 0. So the probability of drawing a 1 on the second draw given the first draw is 0 is 1/2. And the probability of drawing a 1 on the second draw given the first draw is 1 is also 1/2. So here the first draw and the second draw are dependent because the occurrence of the first draw does not affect the occurrence of the second draw, because basically what we took out from the first draw will be returned. Example 3. Items are inspected for flaws by 3 inspectors. If a flaw is present, its inspector will detect it with probability 0.8. The inspectors work independently. If an item has a flaw, what is the probability that at least one inspector detects it? So here, if you work with at least event, usually the techniques to work with at least event is using complement rule. Here is how I solve the problem. The probability that at least one inspector detects the flaw is 1 minus the probability that none of the 3 inspectors detects the flaw. And to find the probability that none of them detects the flaws, we basically use multiplication rule. The question gave you if a flaw is present, its inspector will detect this with probability 0.8. So if a flaw is present, the probability that its inspector will detect it is 0.2. And the probability that none of the 3 inspectors to detect a present flaw is 0.2 times 0.2 times 0.2, which is 0.008. So the probability that at least one inspector detects this is 1 minus 0.008, which is 0.982. So again, whenever you work with at least event, think about complement rules and multiplication rule. So that is everything for today. Thank you so much for watching my video. I hope you guys enjoyed my video and see you next time. Bye.